I mean, at this point, all we've done is just work backwards from using either kind of the reverse power rule, looking at what you know about finding derivatives, and then working backwards. Essentially, that's all we're doing, right? Like last time you wrote yourself, I didn't write it on this one, I wrote it on the other one over here somewhere, but this is where I wrote it, I think. You wrote yourself power rule here, working backwards. You wrote yourself a few other kind of rules. Not that we want to memorize rules, we want to just look for the pattern. You want to understand the notation. Finding the derivative of something. Derivative of a function with respect to a certain variable. We're going to do now the integral of a function with respect to a certain variable. The dx here, you can think of it the same way you think of the dx there. You're basically just saying what's the independent variable in this situation. This notation dy dx comes from change in y, change in x, delta y, delta x. This kind of comes from the same thing. At this point, we don't see where this comes from, but it does come from, dx comes from change in x the same way here. This symbol actually comes from the sigma symbol you might know from before. You're summing up something. When we get into the middle part of this unit here, we're going to look at what it actually represents in this situation. Okay, so we're kind of doing the abstract stuff first. The only technique you're going to have, or you're going to look at, is what's called substitution. We can look at that in a few minutes after you've kind of done a few more of these to warm yourself up here. These ones, I mean, don't forget that a technique you could use is just using algebra first before you find the integral. This looks like something that if it was finding the derivative of this, you could use the chain rule. But here, the only thing you can use at this point is to just expand the thing. X to the fourth plus 2x squared plus 1. And then find the integral of that, which I'm sure you can do. You can divide. You can simplify this to a single expression, right? If you have something times that square root, you can make this square root of x squared times x, put the x inside the square root, dx. So you could make it integral of square root of x to the third dx, or in other words, write it as a power, which would have been quicker the other way here, x to the 3/2. You could have done that right off the bat here and just thought of this as x to the 1 times x to the 1/2 is x to the 3/2 and just add them together. However you do it, but once you make it into this, then you can use your power rule. The fractions are tough with the power rule. What do you do if you're finding the integral of, say, something like that, x to the third? Yeah, 1 over 4. So I would probably do this in this order. I would think of what the power is first, because then you need the reciprocal of that. Okay, I would think about what's the power first, and then you need the reciprocal of that over here, especially when it's something like this. So I would think, what power do I need here? It goes up by 1, right? When you find the derivative, it goes down by 1. When you find the integral, it goes up by 1. So this is x to the 5 over 2. And in front, then we need the reciprocal of that, 2/5. And we need plus a constant, and that gives us the indefinite integral. Again, I told you the term indefinite integral. This is indefinite because it's not evaluated for any specific values. Just again, like the derivative could be just the derivative of something in general. The derivative of x squared is 2x. Or it could be, if this is f of x, the derivative f prime of x is this. But somebody might say, what's f prime at 3? Well, it's 6. It's a specific number. It's the slope at a certain number. This is just a general expression for the slope anywhere. That's what we're doing here. We're doing this is a general expression for what this represents anywhere. We don't quite know what it represents yet, but we will after. Okay? You need to look back at some of these things. All we're doing is turning around the derivatives that we know, right? If you know what the derivative of sine is and cosine is, you can write some integrals of these. The unfortunate thing is, at this stage, we're not going to know what the derivative of cotangent, tangent. We're not going to know we're not going to know integrals of these four, because we don't know any. Do you know a derivative formula that has an answer of secant? Is there a derivative of something where the derivative of something is secant of x? Yeah, we know something where the derivative is secant squared. That's why down here we can do the integral of secant squared, because we know what should go in there. What should go in here? Tan, right? You can't, right? Because it's inside of this derivative thing, right? You can't put it in there. Once we do this technique of substitution, we will be able to do it. But for now, we can only do things where all we're doing is turning around the derivative formulas we know. So if we know that the derivative of tangent is secant squared, we know the integral of secant squared is tangent plus a constant, right? That's all we're doing here. You might have to switch the negative sign around or constants or anything. That's fine, right? If you know that the derivative of sine is cosine, then the integral of cosine is sine plus a constant, right? If you know that the derivative of cosine is, what's the derivative of cosine? Negative sine. Then you can do that, because the derivative of negative cosine would be positive sine, right? So if you want this, then what's this integral going to be? What's this integral going to be right here? Negative cos x plus some constant. It's nothing magic. It's just turning around the things that you theoretically already know. And then once you know that, you can evaluate the other things here, right? This first section is just about turning around the derivative formulas. This is probably more questions than we need here. Just to frustrate you, I said that, don't forget you can use any algebra that you've learned before, including grade 12 trig identities. Lots of fun for people who haven't done that yet, but you're just getting to it now, so don't worry too much. I don't want to get too hung up on using that. I wanted to put this in so that you realize, well, you could do that, right? Like, there's an identity for sine of 2x. You can change this and put that identity in there, right? You can replace this with sine of 2x is actually equal to 2 sine x cos x. That's a trig identity. If you haven't done grade 12 trig identities, you'll get to that very soon if you haven't done it yet. That's on. You're welcome to look at the Math 12 trig identity formula sheets. There's some that you do know already, like this. If you want the integral of dx over secant, what you could think of it as 1 over secant, and you could make that. What could you make that into? Yeah, just make it into cosine. Like, you might have to change things around first, and then that's one that we did up above, right? What's the integral of cosine? Is it negative? I'm asking you. No, it is not. Plus a constant. Okay, and then this one up here, once you use that trig identity, I don't know why I started the next question without finishing this one, but you can cancel things just like before, right? The integral of 2 sine x dx, and then you could make it 2 integral of sine x dx, which is, what is that? Yeah, we want the 2, and we want the negative, and we want the cos here, plus a constant, right? So you can do quite a few, as long as the quite a few are set up carefully by someone so that they work out with these trig identities. Right, if we just said integral of random stuff here, probably you couldn't do it. You'll have to think of this along the lines of, how you spent all those years learning to factor things? Learning to factor like 2x squared plus 7x plus 3 or something like that. And you learned how to factor. The thing is, most quadratics you make up don't factor, but you still learn to factor because it's a technique that works sometimes and it's useful. It's the same thing here. Right now, just working backwards, it relies on you knowing the connection, which is good because they are connected. Work on that for 10 minutes or so. Some of the questions throughout there. Check the answers, and then we'll look at integration by substitution in a few minutes.